Hello viewers, welcome back to the course on matrix computation and its application. So in the previous lecture we have discussed about the vector norm defined on a vector space. So today in this lecture we are going to discuss matrix norm. So let's start with that. So in the previous lecture we have discussed that for any vector v that belongs to Rn or a set of polynomial or a continuous function. So this is things we are defining for. Then we have discussed that we can define the vector norm. So this is we have defined for any v belongs to v. This is my vector norm, and we have discussed one norm or infinity norm or two norm, and in the end we have discussed that we can define p norm. Now these things we have done there, and now we want to define that the same thing is applicable for any vector belongs to complex vector space. So now for any complex vector space, we call it Cn, defined over the complex number C. Now the same things is going to happen there, that for any x belongs to Cn. So this is my x vector coming from this one. Now in this case also we have to discuss, first thing is that this will be greater than or equal to 0, and if this is 0, that implies x is 0. Second thing is also that if I take any scalar alpha, that is equal to the norm alpha and then this one. Now the alpha is a complex number, and the third one is that if I take any two vectors, then this is equal to, so this is also true in the case of a vector space that is defined in the complex plane. Then we also discussed the famous Cauchy-Schwartz inequality. So in this case, for any u and v that belongs to a vector space v, then we can generalize this one, that u taking the inner product, so this is less than the norm of u and the norm of v. So this is also we can generalize in any of the vector space, and inner product we know that we can define in with the different norms, or maybe we have discussed that the inner product, we have seen that how we can define the inner product when we change the vector space. So these things we have already seen. So now I want to discuss that what is going to happen when we are taking a vector. So suppose I take a vector v that is 1 plus I minus 2i 3. Suppose I take this one that belongs to C3. Now I want to define its one norm. So, one norm in this case it will be taking the modulus value or the magnitude of 1 plus I, this one. Now, it is the magnitude of this. So, A plus I B, and if I take the magnitude, then it is A square plus B square under the root. So, that we already know. So, it is in this case it will be, because this magnitude is basically, suppose this is my complex number A, so this is A B, then this is B. So, I know that this value is A square B square under the root. So, this is the magnitude of this one. So, now from here I can write this as root 2 plus, now this is just I will get 2 and plus 3. So, it is 5 plus root 2. So, that is my one norm for the vector space or for a vector in C3. Now, the same thing I can define for the 2 norm. So, 2 norm is 1 plus I square minus 2 I square under the root. So, this one I can define, and from here you know that this is under root 2 square. So, it is 2 plus, now it is magnitude is 2. So, it is 4 and this is 9 under the root. So, it is 15 root. So, this is my 2 norm, and I can define similarly I can define infinity norm. So, infinity norm will be the maximum of 1 plus I magnitude minus 2 I and 3. So, it is again I am taking the maximum of this one. So, it is root 2, it is 2, it is 3, and that is 3. So, I am able to define the infinity norm, the 2 norm, 1 norm of any vectors that is coming from the C3. Also, one more thing I want to discuss, I want to see what will happen when I take 2I multiplied by V. So, this one I want to see. Then by the property, this property we are going to use, it should be equal to 2I modulus value, this one. Now, suppose I take for 1. So, in this case I am taking 1 norm. So, here it is should be 2 and that should be 1 norm, and it is 2 into, so 1 norm of this is this. So, it should be 5 plus root 2. So, that should be the value. Now, if I take 2I multiply by V, then it is going to be 2I 1 plus I 2I minus 2I, and so it is becoming 6I, and from here it is 2I plus 2I square. So, 2I square is minus 2 plus 2I, and now from here it is minus 4 plus minus 4 into I square. So, it is 4 and it is 6I. Now, I define 2I 1 norm. So, it is minus 2 plus 2I plus 4 6I, and here it is 2 square plus 2 square means 4 plus 4 8 under the root plus 4 plus 6, and it is going to be 10, and if you see from here it is 10 plus 2 root 2, and that is 10 plus 8 root 2. So, this is same as this value. So, in this case what we have seen that this modulus value we have to take when we deal with the complex numbers. So, this is one of the example we can define in complex vector space. Now, one thing we want to discuss is that now we are able to see lots of norm. The vector norm I have defined 2 norm, I have defined infinity norm, or maybe I can define p norm. Now, it may happen because we have seen that for any vector these all norms are different. So, the question comes that it may happen that in one norm, if I am taking the convergence of the vectors, then it may happen that in one norm it is very high and in another norm it is very low, or in one norm it may converge and if I take the another norm it may diverge. So, these things generally do not happen. So, from here we have a very important condition about that for finite dimensional vector spaces, all norms are equivalent. So, all norms are equivalent. So, what is the definition of this one? Now, from here I can define that two norms, suppose I take A and B, two norms. So, two norms are equivalent if there exist positive number. A positive number means positive real number. Suppose I take alpha greater than 0 and beta greater than 0, such that if I take, suppose I take the B norm, then it can be written as alpha times A norms and beta times A norm. So, if we are able to write this one, then we say that these two norms A and B are equivalent. It means that their value, the value of a vector in one norm is bounded by the values of the same vector in another norm. So, that is called the equivalence relation. Now, based on this one, now let us define. So, once we have defined the vectors norms, then the next question is that how we can define the matrix norm. So, we want to define a matrix norm. So, now what we are going to do is matrix norm. Now, because matrix is made up of vectors, so we can define the matrix norm as, so I am defining for any matrix A. So, this matrix I am taking, so it can be a rectangular or a square matrix, does not matter. So, for any matrix A, we define the norm. We define a function that is, we are defining from the, so it belongs to the space of order m cross n, and it can be a real and the complex, so it does not matter. So, we are defining a function this over the space, vector space of matrix m cross n to a real number So, this is basically I can say that positive real numbers or a real number R. So, we define a function is said to be norm if satisfies the following conditions. So, we are defining on the set of all the matrices, and this can be real or it can be complex. So, these are the following conditions. First one is that again if I define the norm of a matrix and it is always greater than or equal to 0, and if the norm is 0, which implies that A is a null matrix. It means that A is equal to 0 matrix. Second one is that again if I take some scalar alpha multiply with this one, then this is equal to magnitude of alpha, this value, where alpha is a scalar. So, it can be real or complex. Third one is if I take two matrices for any A and B belongs to Mn. So, of course, if I take the sum, then it should be of same dimension. So, if I take the norm, then it is equal to the norm. So, this is the triangle inequality. And this is true for all A and B belongs to, so this is already I have written that for any this one. Now, fourth one. So, the fourth one is I take A into B. So, I am writing that A into B only it can be written if it is. So, if I can write that if the product of A and B is possible, is defined or possible, then I can write A, B, the product of A, B taking the norm, then this is less than or equal to the norm of A and norm of B. So, this condition if you see, this is the analogous to the Cauchy-Schwartz inequality, because in the Cauchy-Schwartz inequality we are also taking the dot product of the two vectors, and then this gives you this condition. So, now this condition is happening in the case of matrices, but this is only possible when A and B is defined. So, if I take all the set of all the square matrix, then it is okay, no problem. But if the matrix is a rectangular matrix, then we have to take care about this product. So, these are the four conditions we have to define. So, after defining this one, now we can define the distance between two matrices. So, I can define the distance between suppose A and B, then it becomes A minus B norm. So, then I can define the distance between two matrices. So, once I able to define a norm which satisfying all this condition, then we say that this norm is well defined. So, let us discuss about the different type of norms. Now, first of all, so I will define norms. Let us I take a matrix A and suppose its dimension is m cross n. Now, I define its one norm. So, one norm also we have defined for the vectors. So, the similarly I am defining the norm 1, and here the one norm is a maximum column sums. So, it is what it is? It is I am taking the maximum over J summation. So, a matrix A can be written as Aij, where I is moving from 1 to m and from 1 to n. So, it is of order m cross n. So, I am taking the column sum. So, I am taking first column and then taking the magnitude, and I is moving from 1 to m, whatever the value is there, and then so first column taking the sum, second column, and then taking the maximum of all this one. So, this is the maximum column sum. Similarly, so this is one of the norm that we can verify that it satisfies all this condition. So, this is the one norm. Now, similarly I can define another norm, and that we have already seen is Frobenius norm. So, Frobenius norm we have seen in the inner product of the matrix. So, this is you know that this we have taken from finding the trace of A transpose A or trace of A star A. When the matrix is a complex, then we take the star and then under the root. So, this one we taking the from the inner product. So, this norm is called, we know that this norm is called the Frobenius norm or Euclidean norm. So, this is the another norm we have defined. So, this norm actually we know that this is equal to taking the magnitude square and then under the root. So, that is equal to this one. Now, third norm we are going to define infinity norm. So, infinity norm is again it is the maximum row sums. So, in this case I am taking the maximum over the rows and taking the summation of A I j, and j is moving from 1 to n. So, it is called the maximum row sum. Now, so these sums we can define. So, for example, now I take a matrix A. So, just I am taking 2 by 2 matrix maybe. So, I just writing 2 plus I 3 minus 2 and 1 minus I. So, this is I am taking the complex matrix. So, I want to take one norm. So, one norm I have just defined taking the maximum column sum. So, what I am going to do is that I am taking the maximum of the column sum. So, first I am taking this column and then this is my column. So, this value is I am taking 2 plus I modulus value plus minus 2 So, this is the first sum of the first column, then 3 1 minus I this one. So, from here I can write that this is equal to maximum. So, 2 plus I, it is 2 raised to power 2 4 plus 1 5 under the root plus 2, and it is 3, and it is 1 plus 1 under root 2. So, it is this one. So, in this case the maximum value if I take, so this one we can find. Now, root 5 I can take from this one. So, this is we are defining. Now, five root or maybe so root 5 is 2.236 and root 2 I know is 1.414. So, from here I can see that I can take the maximum value. So, it is 4.236 and this is 3 plus 1 4.414. So, if I calculate this value, then this is my 414. So, that is my one norm. Similarly, I can define another norm. Maybe I can define Frobenius norm. So, in this case what I am going to do is that taking the modulus value of each and square. So, it will be 9 plus 4 plus 1 minus I and then under the root. So, it is I am taking first I am taking the magnitude. So, its magnitude is 4 plus 1 5 root 5. So, it will be 5 plus 9 plus 4 plus 2 root. So, 14 plus 18 20 root 20. So, that is my in this case is a Frobenius norm, and Frobenius norm if you see the root 20. So, I can take the root 20 value. So, it is equal to approximately 4.472. So, this is the Frobenius norm. So, one norm is 4.14 and Frobenius is coming 4.472. Similarly, we can define infinity norm. So, now one norm is there, then now I am taking the infinity norm. So, it is the maximum of the row sum. So, 2 plus I 3, this is the first row, and minus 2 1 minus I this value. So, it is again I am taking the maximum value. So, it is again under root 5 plus 3 and this is 2 plus root 2 obviously. So, this value is 3 plus root 5. So, that is my infinity norm. So, this way we can define the different type of norms for a given matrix, and I have taken this matrix as a square matrix with complex eigenvalues or complex entries. But these things can be done for any matrix. Maybe I can take example of a matrix A which is like 2 1 0 3 minus 2 minus 4. So, this is 3 cross 2 matrix. The same way I can define these values. Now, after defining this, now I want to see, because we have seen here that the matrix norm and the vectors norms looks like similar, then we want to define one condition here, is that because we have seen the Frobenius norm in a vector form also and the matrix form also. So, I would just want to define that now, since if I want to define, suppose I take a matrix A, any matrix, now for any matrix A, I define Ax. So, Ax, I know that for any matrix A, Ax is a vector, because I am taking x as a vector. Suppose x A is from m cross n, and then I definitely x will be n cross 1. So, in this case I can say that it belongs to Rn, and I am taking this column vector. So, I can write like this one. Now, suppose I take its 2 norm. So, I just taking the 2 norm. So, I know that this is equal to summation taking the multiplication and then taking the square of that. So, this is basically I am writing A I star x multiplying, taking square, and then, so this one I can write here. Now, I can apply, because this I know that the Cauchy-Schwartz inequality. So, from here I can write that this is always less than equal to summation so I have to take, and then this value, because this x is complete x I am taking. So, this can be less than equal to this value by the Cauchy-Schwartz inequality, and this one I can write again as, because x is, so this is sum is going on the matrix now, and this x can be taken out. So, this will be equal to summation square, and now I am defining here. So, this is 2 norm basically I am taking, this is a 2 norm. So, this one, this value, and what is this? It is just we have taken that this is equal to Frobenius norm. So, it is not the 2 norm, it is just we have written Frobenius norm. So, from here I can say that 2 norm is less than equal to Frobenius norm and these 2 norm. It means that if I take the Ax taking the 2 norm, that is always less than equal to the Frobenius norm of A into the 2 norm of x. It means that 2 norm of the vector and the Frobenius norm of the matrix are connected to each other. So, such type of connection we call it the compatibility. So, let us define one more term is here, the compatibility of matrix of matrix and vector norm. Now, the norms of a matrix suppose I take the matrix A, so that is I write this one is said to be compatible, or I can say consistent with a vector norm if, so compatible with a vector norm of, suppose I take x, that is if, so I take the matrix A, then Ax should be defined. So then I take its vector norm, because it is a vector, so I am taking the vector norm. So if this is less than equal to, so this is the matrix norm I am taking and this is the vector norm I am taking. So the norms of the matrix, so this is a matrix norm M, is said to be compatible with the vector norm of X. So this is vector norm I am taking if this is condition, this condition is satisfied. Okay, so in this case both the norms are coming, M is also coming and V is also coming. Now from the previous one we have seen that the 2 norm of the vector is compatible with the Frobenius norm of the matrix. So from here, from previous example, we can say that 2 norm and Frobenius norm are compatible, because I can write Ax 2 norm that is less than equal to Frobenius norm and 2 norm. So this is the way we can define. Now we have defined the Frobenius norm and we have defined the 2 norm. Now the next question is that how we can define the 2 norm of a matrix. So let us define from here, we define the 2 norms, because I want to see what will happen if I, instead of Frobenius, I just take the 2 norm. Now from here I just define that, from here I can write Ax 2 that is always less than Frobenius norm, and from here using this condition I can define a norm. So from here I define a norm as maximum, because in this case I am taking that this norm is always greater than equal to this value. So if I take the maximum of this value, then this will be equal to this. So I am taking Ax over x and taking the over all the x. So from here I can define this one norm, and this norm we are defining. So now this norm is, again it has a norm. So this norm is called the subordinate norm, and it is coming from the vector norms by taking this one. So this is a subordinate to vector norm, subordinate to vector norm. So, I have taken the idea from here and then we define a new norm that is represented by this one. So, this is a new norm I can say. So, what is this norm? Now, suppose I take 2 here. So, this is equal to maximum of x to 2. So, now from this value, this one I can define 2 norm of a matrix. So, whatever the vector norm I am taking, based on this one I can define the 2 norm. As we have seen in the term of Frobenius norm. So, Frobenius norm we have taken with respect to 2. Now, from that idea I want to see what will be the 2 norm of a given matrix with respect to the 2 norm of a vector. So, this is a norm definition of a norm. So, let us see that how we can find this one. So, for example, now if you see from here I am taking a x, taking its norm, multiplying a x, then taking its norm and taking the maximum value. So, if you see from here, then we are blow up the value of x because I am taking the maximum values. For example, let us define what is going to be a 2 norm here. So, this is called the 2 norm of a matrix A. Let us do. So, suppose I take a matrix A, I just take 1 minus 1 0 2 and I want to define its 2 norm. So, this value I am going to take, it will be maximum of x now. If I take the normalized vector so that its norm is 1, then so it is normalized vectors, then this become maximum over all the x whose norm is 1 2. So, this is 2. So, this is another definition of this one. Now, I will use this one. So, I have taken A here. So, let we take x as I just take 1 by root 2 minus 1 by root 2. Suppose I take this value. Why I have taken this one? Because its 2 norm is 1. Now, I multiply by A x. So, A x is 1 minus 1 0 2 and minus 1 by root 2. So, from here I can write that it is 1 over root 2, 1 over root 2 plus 1 over root 2. So, 2 over root 2, this one I can write, and this will be 0, it is minus 2 root 2. I get the new vector here. Now, I define its 2 norm. So, it is, if I take, so it will be square 2 by root 2 square plus minus 2 by root 2 square under the root, and that is I am taking it 4 by 2 because I am taking its square. So, 4 by 2 2 plus 2 4. So, the value is coming 2. So, now my A x 2 is coming 2. So, from here I can define, so I can define from here A x 2 by that is basically 2. So, I started with a vector whose norm was 1 and now I defined this one and its value became 2. So, now maybe I can choose another vector, choose another vector. So, I take now x is equal to, instead of 1 I just take 1 by root 2, 1 by root 2. I just take this vector now. Now, I know that this is 2 norm is 1 here. Now, Ax will be again, so it is 1 minus 1 0 2, 1 minus 1 0 2 and 1 by root 2, 1 by root 2. So, this is in this case now I am taking this value here. So, it will be 0 here now, because 1 by root 2 minus 1 by root 2, and this will be 2 by root 2. I got this value, and now I take the 2 norm of this vector. So, if I take the 2 norm of this vector, then this is equal to 0 plus 2 root 2 square under the root. So, it is coming 2 root 2. So, this value now becoming 2 root 2. It is less than 2, but greater than 1. So, we have started with a vector and its value slightly increased to this one. Here we have started with a vector whose norm is 1 and its value slightly changed and became 2. So, I will take all these vectors and then take the maximum. So, this way we can find out the norm, but we cannot compute over all x such that norm of x is 1, because there are infinite number of vectors there. So, these things we cannot compute for all x to find out, but ultimately we are reaching toward its maximum value, and whatever the maximum value we are going to take, that will be the 2 norm in this case. So, from here let us see that how we can do this, define the 2 norm here, because this concept is okay, but it is not possible for us to find all these vectors x whose norm is 1 and then finding these values. So, let us define that how we can take the 2 norms in this case. Now, let us take this one value. So, the question is how to define 2 norm. This is what we are going to do. Okay, so let us see. We know that for any matrix A, it is suppose m cross n, and my suppose n is n cross 1. Let us define A x and take its 2 norm. Then, so let us write in this way. I define 2 norm this one. So, that will be maximum A x square. This I can define, I just taking the square. Now, from here this one I can write from that this is can be written as maximum this value, and now A x norm square, then I can take the definition of inner product, because this is coming from the Euclidean norm, from the inner product is an induced norm that I know. Then I can write here that this is A x this value. because we know that x y inner product, it is equal to x transpose y, and that is equal to norm of x square, that we already know, and it is coming as a 2 norm, or maybe I can define like this one. So, this value I am taking, that is equal to maximum 1, and this is the inner product I am defining. So, I can write here Ax transpose Ax. This is again taking the maximum, and I can write here x transpose Ax. Now, this matrix I got, that is A transpose A. Now, from here I know that now for any matrix that is A of order m cross n, does not matter, A transpose A will be always, A transpose will be n cross m, and this will be m cross n. So, A transpose A is always n cross n. So, it is always square matrix. So, A transpose A is square matrix. One thing is that also A transpose A, if I take the transpose, then this becomes A transpose transpose, and that is A transpose A. And from here I can say that A transpose A is a symmetric matrix. This one. So, now it is always square matrix, it is always symmetric matrix. One more thing is there. Now, I know that this is symmetric matrix. I also say one more important property I am saying about this one, that A transpose A is always positive definite. Positive definite means all its eigenvalues are positive. So, this is always true. How it is true? Because I know that A transpose A, suppose I take any x is equal to lambda x, this one I can write as a eigenvalue. From here I can write as a x transpose A transpose A x, it can be written as lambda x transpose x, and from here I can write that lambda is equal to x transpose A transpose A x divided by, so this is basically x transpose x, so it is x transpose x. So, I can write that this is equal to square. Now, from here I just complete this process. Now, I can, so from here I can write, so this is the norm. So, suppose I taking the all the x whose magnitude is 1, so this can be removed. So, from here I can, because it is positive always, so this can be written as Ax transpose Ax divided by square, and this again can be written as Ax square divided by square. So, it is always positive, and from here if it all the eigenvalues are positive, then we know that this is positive definite. So, this matrix satisfying all this condition, that it is a square matrix, it is a symmetric matrix, and this is always positive definite. So, these things we defining here. Now, let I take A transpose A is equal to matrix B. So, from here I can write that A can be written as maximum over all the x such that x transpose be x. This one I can write. Now, this matrix is a positive definite and everything is there. Now, from here I can write. So, now and this one I am taking is equal to 1, that is equal to maximum A transpose A x. Now, from here we know that for any x we can normalize it to make sure that its norm is 1. That we can do. Now, from here what I am going to write is that this thing I am going to write maximum. Now, this is my taking the same way as we have done here, that any matrix can be written like this way. So, I can define this as maximum over all xi. Suppose I am taking xi. Now, A transpose A I can write as xi for any eigenvector. I can define as a lambda I xi. For lambda I is the eigenvalue and xi is the eigenvector. So, this concept we already know, and it is a n cross n matrix. So, it will going to have a n number of eigenvalues, and then we can have the eigenvector, corresponding eigenvectors. So, this is true I is equal to 1, 2, 3 up to n. Now, from here working with the same concept, I can write lambda I is equal to xi transpose A transpose A xi divided by xi transpose xi. Now, we can normalize xi, that becomes 1. So, from here I can write that this lambda I is equal to xi transpose A transpose A xi. So, from here these things can be written. So, I can write this as 1, 2. So, I can write equation 2 can be written as now I am taking the maximum, and this can be written as a lambda i's, because I have shown that xi transpose A x, and that I taken maximum of all the xi's, and that is this one lambda i's. So, this I can write the lambda i's over all i's, because I am taking the maximum over all xi, and that is the eigenvectors. And from here I can write that this is equal to lambda maximum, where lambda maximum is maximum eigenvalues of A transpose A. And from here I can define 2 norm as square root of maximum. So, this way we can define the 2 norm of a given matrix this way. So, we will stop here now. So, in the today lecture we have started with the matrix norm, that how we can define different type of matrix norm. Then we have discussed that how matrix norm and the vector norms are compatible to each other, and then in the end we have discussed that how we can define the two norm of a given matrix in the terms of the eigenvalues. So, in the next lecture we also continue with this one. So, thanks for watching. Thanks very much.